Okay, so we were in section 5.6 when we ran out of time last time, and so we're going to finish up 5.6. We're going to talk about this new idea called moment of inertia. This is a physics concept. This is not a physics course. The reason I'm going to bring this up is because it's a good opportunity, I think, to talk about an unexpected Riemann sum. And so I think it's worth discussing, if only for that. But also, it ends up with a definition that's going to come up in math classes, and that is going to be pretty useful to y'all when you take your corresponding physics classes, etc., engineering, what have you. Okay, so some old news. When you have a circle, arc length is radius times angle. I hope everybody remembers that. It's a standard high school geometry fact. I can then just take a derivative of both sides. Right, and the idea is if you have something moving around that circle, the rate of change of the distance is equal to the r times the rate of change of the angle. And notice that this, on the left, pre-existing concept, what we call speed, right, distance per unit time. Notice that then there's kind of a related idea over here on the right, not rate of change of a distance that I use to identify where I am, but rate of change of an angle that I could think of as a way of describing where I am in its own way. It's kind of a different sort of a coordinate. So this is it's a speed in the sense that it's a time rate of change of a coordinate, but it's not a distance speed, it's an angle speed, and so that's the term angular speed. Sometimes people sloppily call this angular velocity. I think angular speed is actually makes more sense here. So what I want to consider now, a related question, is suppose I have a big solid like this, and this solid is rotating around this axis, the same axis that defines the circle there. Great big lumpy solid rotating around that axis. How would I compute kinetic energy for this movement? Side note: if you don't know what kinetic energy is, no problem. It's a way of representing how much. One way to think of it: how much work it takes to get a certain motion happening. Okay, but again, not a physics class. Don't worry about it. So the standard formula for kinetic energy, if you want to understand, how much kinetic energy does this have, is right there: 1/2 mv squared. High school physics. Reference. Here's the problem. If you look at this solid lump of mass, pieces of mass that are over near the axis, like this little lump of mass right there, it only moves that relatively short distance in the time it takes for our solid to go around one time. Whereas, by contrast, this piece of mass over here, it travels a much greater distance in the same amount of time. That is, this red piece of mass is moving faster. So, do I use the blue speed or do I use the red speed? If I'm going to use this formula that makes the reference to speed, which speed? Well, that's a rhetorical question. I can't just pick one, right? The whole point is they are moving with different speeds. I cannot use this formula. It doesn't work. Right. Okay. So here's the idea. Here's where the Riemann sum comes in. This is another opportunity to do a chop it up, add it up, whole is the sum of the parts, however you want to say it. And the idea is let's take our solid, break our entire solid up into little pieces. And then on each little piece, I can talk about, well, how much kinetic energy does each little piece have? No problem. Each little piece, it's small. All the pieces of mass in that one little teeny tiny little piece of the solid, yeah, they're all moving with close enough anyway, same speed. So 1/2 mv squared works just fine. This little piece of kinetic energy is easy. And then if I want to add up over the entire solid, sure, go ahead, integrate, add up over the entire solid. So, again, this is the part that I think is the most interesting to Math 219, is that we don't think it doesn't look like a Riemann sum problem, but it really is. It's just that the object the quantity that we're chopping up into little pieces is something we can't physically see. Right? Okay, now some work follows from this. Again, recall that for our little piece, we can use the linear formula for kinetic energy. 1/2 mv squared. The mass, of course, is just however much mass is in our little piece, dm. And then we kind of move things around a little bit. Don't forget our speed is r omega. And when you have something that's rotating around an axis, the angular speed is a constant. That's why the mass doesn't break apart. Right? Everything's kind of going around at the same. 2 pi per period is the angular speed for everything on the solid. So, being as it is a constant, I can factor it out, like I've done there, and that leaves me then with this expression. Now, what am I going to do with this expression? What I'm going to do is, this will make sense in just a moment, I'm going to take this part here. Whatever that thing is, it's a weird integral that remains. I'm going to call it I temporarily. Bear with me. Having called that I, now look at our formula. Oh my gosh, our formula looks just like the old kinetic energy formula, except instead of linear velocity, now I've got X seemingly in the same place in the equation, playing the same role. Now I have angular velocity, angular speed instead of linear speed. Right? So it's like, we're on track to saying that this is kind of this right here is sort of an angular version of our old kinetic energy formula. And so in the same sense that this omega is angular speed, it's kind of like speed, but in an angular sense instead of a linear sense. Along those same lines, looking at the fact that this I thing here is sitting right in there, playing an analogous role to mass, it's like this thing is an angular analog of mass, in the same sense that omega is an angular analog of speed. Now, that's just a, hey, check it out kind of observation. We didn't prove anything there, right? But if, let's say it this way, if you define this thing here to be something, we give it a name, we call it moment of inertia, right? And then if you interpret it as, it's the thing that goes in that position in this formula for computing kinetic energy, then everything fits together. And so this object, this construction, this weird triple integral here, it just kind of was what was left over when I separated everything else out. This thing is natural, right? It fits in a really natural way with other existing natural concepts. So it's a big idea in physics if you're talking about mechanics, moment of inertia. And this is why we care about it. It's where it comes up. Okay, now bad news. Going back to our picture here, notice R is the distance from wherever you might happen to be, whatever point you're at that's, rotating around, distance to the line, the axis that you're rotating around. Notice it is not necessarily the cylindrical coordinate R. And that's confusing. Case could be made that we shouldn't use R here with exactly that point in mind. In fact, I believe I've made exactly that point in the past. So why am I using R incompatibly with my previous suggestions? It's because, everybody else does. It's pretty standard notation. Y'all are certainly going to see it. And I suppose I could invent my own standard, and then you'd think, you get used to that, and then you get out into the real world, and the whole rest of the world would look weird. So I didn't think that was a good choice. So what you have to do is just keep it in mind that when you see that R in that equation for a moment of inertia, integral R squared dm, when you see R there, don't assume that it is the cylindrical coordinate R. Now sometimes it is. If you're rotating around the z-axis from some point, wherever you might happen to be, that distance there from that point to that line truly is the cylindrical coordinate R. It is exactly what you think it is, and we got lucky. right? But very often, usually, in other words, in any other case other than that one line, namely the z-axis, if you're rotating around any other line, it's just not true, right? R, for example, in this scenario, distance to that line right there, well, that's not the cylindrical coordinate R. This isn't the cylindrical coordinate R. This isn't the cylindrical coordinate R. Each one of these is its own little separate little geometry problem. Right? So anytime you are computing a moment of inertia, you've got to look at the question, think very carefully about what the axis is, and then think through how would you compute these corresponding formulas. Again, usually a matter of sort of looking at the picture and, maybe you might have to do a little bit of geometry, but very often it's just a matter of seeing it straight off the picture. Okay. All right. So let's do one. Here we go. Here we go. We're going to look at this solid right here. Well, solid region in the plane, that is. There's our two-dimensional region. And I've got mass distributed through that region as given by this formula here. So there's density. That's, of course, mass per unit area, because this is a two-dimensional area. And, all right, how do I find moment of inertia? Specifically, moment of inertia around the x-axis. So here's our axis of rotation. Now, you could view that this two-dimensional thing actually is rotating around the x-axis. That would make the problem feel like a three-dimensional problem. The thing is, you don't have to. Moment of inertia is still there, even if the thing isn't actually moving, right? So we don't need it to actually be rotating in the same sense that mass doesn't have to actually be moving to still be mass, right? Moment of inertia, likewise, it just is. So this is a two-dimensional problem, and now we just have to ask, all right, how do I compute distance from a generic point in my solid, x comma y, from that point down to this axis of rotation? What is that distance? And you can see right here in the picture, nothing to it. The distance from a point to the x-axis, so y. No big. How we doing? Is everybody with me? You could get careful if you really wanted to be careful about it and say, well, here's the thing, y is a coordinate. Coordinates can be negative. The r is a distance. It needs to be positive, so maybe I'd better say absolute value of y. Well, no problem. Here, y is always positive in this domain, so I don't have to deal with that here. It's not an issue. Okay, for this example. Okay, so per that observation, r is just y. Let's see here. We have mass is density times area. Density was given. Density is 2 plus cosine x. And we have a double integral, and off you go. Compute. Everybody okay? All right. Okay, so that's moment of inertia. That ends section 5.6. That ends our time in chapter 5, and we move on now to chapter 6. Let's see here. Before we get into chapter 6, I guess I'll pause for a quick second and remind y'all that we do have a test on Friday. I can't remember if I gave y'all that reminder in Monday, our last class. But so don't forget, we do have a test on Friday. Of course, what we're doing today is not fair game, right? Per the calendar. Remember, we have I don't have it up handy, but the fair game material for exam 2 is what we finished by Monday, this recent past Monday. Okay. All right. Okay, so chapter 6. We're going to define a new kind of integrals. Quickly taking stock of what we've done in the past. Y'all came into this class understanding single variable integrals already. Early in chapter 5, we defined double integrals. fundamentally different thing, but also very, very analogous concept, right? I mean, a double integral is still chop it up, add it up. The whole is the sum of the parts. It's just over two-dimensional regions instead of one-dimensional intervals. Cool. Triple integrals. Again, fundamentally different thing in the sense that it happens over a solid. We're chopping up in three different directions, right? Very different in that sense. But still, the whole is the sum of the parts. Chop it up, add it up, say it however you like. Then there were computational methods, spherical coordinates, change of variables. Those are all just computational methods. So fundamentally, we've seen three kinds of integrals. Single variable, double integrals, triple integrals. We are now going to add to that list a new kind of integral, something called a line integral. First thing to notice is that the integrals that we've seen to this point, they're all, what I'm going to say, the domains are of the same dimension as the world that they live in. Take a double integral, for example. When you're doing a double integral, like, let's see, we were just looking at a double integral. Here you go, double integral. This is a two-dimensional region, and it is in a two-dimensional world. Right? Triple integrals. See, I probably have a picture of one of those around here somewhere. Oh, gosh, do I? Surely, somewhere. Okay, I don't have it. Here you go. Okay, so triple integral, right? And the region we were looking at here, this is a intrinsically three-dimensional solid, and it lives in a three-dimensional world. What we're going to look at now is when there is a mismatch, when the dimension of the domain is different from that of the world that it lives in. So here we are going to talk about a curve, for example. That curve is what I'm going to call intrinsically one-dimensional. When you're on this curve, there's really only one direction that you can go. Well, and its opposite, of course. Right? Said differently, this domain here, this curve, has a length, which is a one-dimensional concept. It doesn't have an area. Area doesn't make sense on this domain. This is an intrinsically one-dimensional thing. Okay, but you notice that it does not live in a one-dimensional world. It lives in a two-dimensional world. Or, if I were to draw another axis, a three-dimensional world, maybe. Right? But clearly not a one-dimensional world. So we have a mismatch. The dimension of the object itself and the dimension of the world that it lives in, not the same. How do we deal with this? Is what we're going to deal with here. Okay, so let's ask the question: how would I do a Riemann sum if I had some question I was interested in? And again, let's not don't nail down an actual physics problem. But if there's some quantity that adds up over this curve, maybe it's a bent wire, and I want to compute the mass. I want to compute the total mass as a sum of a bunch of little pieces of mass. Right? Maybe there's maybe this is a river, and there's fish in the river, but the population of fish is greater in up here in this vicinity, and it's lower in this general vicinity for environmental reasons, whatever. Right? And I want to compute the total number of fish. Well, I could compute the total number of fish in each little piece along the way, add it all up. Right? So whatever it is I might be wanting to compute, how would I write down this overall strategy of I'm going to chop up my curve into a bunch of little pieces, I'm going to compute whatever my quantity is on each little piece, and then I'm going to add up over all the pieces. And I claim that would look like this. So, all right, I chop it up into little pieces. Let's see here. On each little piece, let's look at this little piece right there. How many fish are in that little piece of the river? Well, in order to understand how many fish are in that little piece of the river, I would need to know how many fish per, mile along the river at that point. How many fish per mile? And then I would multiply that by how many miles, right? How far is it? What is that delta S? So, fish per unit mile times miles gives you fish. Does that make sense there? Okay. Maybe, forget about the river. Maybe this is a bent piece of metal. How would I compute how much mass is in this little piece? Well, mass per unit length times length. Same basic strategy, right? So there's going to be what's eventually going to be our integrand, which is always going to be quantity per unit length, whatever the quantity is. That's going to get multiplied by length, delta S. And then I just add up over the entire curve, and as a whole over the entire curve, we just let I go from 1 to n and add it up. We're going to have some round off errors. We take the limit as n goes to infinity. Let's not worry about the formalities, but as with every other kind of integral we've seen, under nice conditions, that makes all of our round off errors go away. And so this is our construction. Everybody notice that this is really a lot like every other Riemann sum we've written down. What do you think? Everybody all right with that? Okay. Okie dokie. Notation. You can probably see this coming. We're going to use an integral symbol to represent limit of a summation, just like every other integral we've ever seen. We're going to use D as a kind of notational shorthand for the delta there, if you will. That's just notation. It's nothing to worry about. Highly analogous, probably exactly what you were expecting. And then as usual, I need some indication of what my domain actually is. And if my domain is this curve C, then we make that C a subscript in the notation. So there you go. We have ourselves a definition. This notation here is a shorthand representation of the Riemann sum. The chop it up, add it up strategy on a curve. The terminology we use, we call this a line integral. For reasons that will not be clear for a little while, I'm going to call this a scalar line integral. And just to give you a little bit of a preview of why we call this a scalar line integral, it's because, and this is going to seem weird, I apologize in advance, it's because the differential is a scalar. And you might be thinking to yourself, what else would it be? Every differential we've ever seen has been a scalar. We'll come back to that a little bit later. Furthermore, the integrand, scalar. And again, you might be thinking to yourself, what else would it be? Every integrand we've ever seen was a scalar. Anyway, that's why we call it a scalar line integral. We will see a different kind of line integral pretty soon, possibly today. Okay, scalar line integral. Now here's the bad news. This thing here. We don't know how to compute it. Right? And we've been here before. When the very first time we wrote down double integrals, we didn't really know how to compute that either. And we had to get creative and make arguments about how iterated integrals ought to compute the same thing, and I guess we can compute double integrals with iterated integrals, and, we made it work. Can I compute this with a double iterated integral? No, that would require areas. There's no area in this picture, so that's a dead end. What do we do here? This is what I'm going to call an undesirable domain. If you have a curve as your domain, I don't like it. The fact that it's a curve is what makes this integral hard to compute. Right? Okay. Well, what have we done in the past when we've had undesirable domains? We've had a lot of undesirable... Oh, yeah, you have a question.
Yeah, I just have a question. Is like the density function based off the length of the curve, or is it based off just the x or y?
It's based off of length. Yeah, that's a good question. That's right. So this thing that I'm calling a density is always quantity per unit length, and length, specifically this length, it's that little length right there. It's now on this little slice that looks like it's kind of horizontal, and maybe that was confusing. Maybe that makes it look like it's the x coordinate only. No, it's the actual length. And so let's look at this piece over here. Right, so it's that length itself, independent of what the coordinates are doing.
But is density written as a function of f and y?
Yeah, the density is, that's right. So, I mean, let's think about the fish example, right? I mean, you could imagine that the number of a certain kind of fish, whatever fish, that's living in a river would depend on, latitude, right? In northern latitudes, you're not going to get as much of a certain kind of a fish. In southern latitudes, maybe you get more of that kind of a fish. So the fish density, right? Fish per mile of river is going to depend on X and Y, latitude in that case. But it's still a number of fish per unit length. Yeah. Does that make sense? Yeah. Cool. All right. Okay, so we have ourselves an undesirable domain. I don't like the fact that this is it's just weird, right? It's a one-dimensional thing in a two-dimensional world. What do we do with that? We have already addressed this, strategically anyway. When you have an undesirable domain, use change of variables. Whoops, I was in the wrong mode there. Use change of variables. Said differently, view it as an image. Right, that was what we did in change of variables. We took our undesirable domain, we found some way to view it as being an image, and then we did a pullback to rewrite the integral that we started with on our undesirable domain and pull back through the whatever function that is to get instead an integral on this pullback domain. Right? It was very successful. We did a lot of we dealt with a lot of very undesirable domains with this pullback strategy. So the big question then is I got to figure out how can I view a curve as being an image. And here's the good news. We already know how to do, we already knew how to do that. We've done it a bazillion times. That's called parametrizing the curve. If you think about it, that is what a parameterization does. It makes that curve the image. And then whatever the range of values of t is, that's your pullback domain. So we're in business. The undesirable integral that we start with, on our curve, right? I don't like that integral. The domain is all curvy and weird and stuff. I pull back and get instead an integral defined on just this interval there. Much more desirable integral on the t-axis. Now, details. Isn't there a stretching factor or something? What is the stretching factor in this case? Specifically then, if I have a little piece of curve of length ds, and if I want to relate that to a little piece of parameter dt, what is the relationship between ds and dt? They're certainly not the same. Clearly not the same. What's the relationship? Well, I have a pre-existing relationship. Distance is equal to speed times time. Right? Old fact. High school physics concept. I don't even know what you call it. I guess it's math or physics or whatever. But speed is the relationship between distance and time. Speed is what you multiply by elapsed time to get distance. Say it however you like. So that is our stretching factor. That is what we insert into the integral to make it all work. And we are now truly in business. We have ourselves a formula. Here it is. If you want to compute a line integral, that's how you do a pullback right there. And everything's written in terms of t, you notice? This is a single variable integral. Plug and chug. Okay, let's do one. Actually, we're going to do 4. Oh, I'm getting ahead of myself. Real quick. This is a very possibly you're not going to have been concerned about the issue that this will resolve. But I suppose we could have been concerned. Hey, what if you use one parameterization and somebody else uses a different parameterization? You would get different pullback integrals. How do we know who gets the right answer? Is there a correct parameterization to use, right? This is something to be worried about. Good news, it doesn't matter. Any parameterization you use is just fine. So use whatever parameterization you like. Whatever is the easiest parameterization. No problem. Okay, now examples. As is often the case, I'm going to start off with an easy example where some of the tools that we normally would have to hunt for are given. Right? Let's get I want an easy starter example. Let's get a win on the board, and then we'll deal with harder examples after. So I'm going to assume that not only do I have something that's in the shape of a curve, right? But furthermore, that it comes pre-parameterized, right? In fact, it's described by its parameterization. But I emphasize, you will not always get this lucky. The parameterization will not always be given. I just want to get some points on the board. Okay, and given mass per unit length being a certain formula, how would I compute the various things? How would I compute the total mass? How would I compute the center of mass, which has two coordinates, x and y? How would I compute the moment of inertia around, let's say, the x-axis, right? Various different things that I could want to compute for this irregular wire. And notice, mass, center of mass, moment of inertia, all in reference to the same wire, on the same curve, with the same parameterization, for the same range of values of t, with the same density. So a lot of what we're going to do on these 4 questions is going to be all the same. And that's why I want to do them kind of in parallel so you can see the parts that are the same versus the parts that are different. So let's see here. First, let's talk about the Riemann sum aspects of things. I'll go back up to the algebra I just glossed over real quick in a minute. But how do we add up mass? Boom. Whole's the sum of the parts. And of course, mass is density times size. Okay, what is the x-coordinate of the center of mass? It's the weighted average of the x-coordinate. An old formula from before spring break, I think. I can't remember. Maybe it was, anyway, recent old formula. What is the y-coordinate of the center of mass? Well, it's the weighted average of the y-coordinates. Right? All that's old news. What is the moment of inertia? Integral r squared dm. We just talked about that earlier today. Nice general formula. It's always integral r squared dm. You have to interpret r appropriately. Right. Okay, well then, now what? Well, now we've got line integrals. We want to plug into this formula here for computing a line integral, right? I have a bunch of line integrals. I want to be able to compute. This formula here says I'm apparently going to need to know this stretching factor. I'm going to need to know the magnitude of x prime. So let's go ahead and do that. Magnitude of x prime. I can take the derivative. Little calculus there. Take the derivative. That gives me velocity. Of the velocity, I can take the magnitude to get the speed. That speed is my stretching factor. And again, this is the stretching factor that we're going to use for all 4 of these line integrals that we're computing. Let's see here, scrolling down. And let me zoom out so I can fit all this on at the same time. So when I look at this line integral here, for example, and I want to rewrite ds, well, ds is equal to stretching factor speed times dt. And here it is. Stretching factor, aka speed, is this. And you'll notice that same thing happening in here, let me do it like this. You notice that same thing happening here in that integral, here here in this integral, here in that integral. And you see I've just inserted the same exact speed for all of them. Everybody on board? Okay. All right, one other little detail I'm going to mention, and I'm going to zoom back in for this. Further, don't forget, actually I think, no, that's fine. Furthermore, don't forget, when you have a parameterization, let me rephrase that, once you've got your parameterization, maybe it's given, maybe you have to find it. Don't forget what it means. Whatever that first coordinate is, that's telling you what x is. That is the formula for x. That's your pullback for x. That's what you plug in for x when you're doing the pullback. And then, likewise, this thing here is your y. So keep that in mind. In this case, we've got, for this parameterization, x is t and y is t squared. Cool. So, here we go. X is t. Everywhere I see an x in any of these integrals, boom, t. Likewise, y is t squared. Anywhere in any one of these integrals. You just plug that in. So, again, the parameterization, just like a change of variables function, parameterization tells you how to plug in. Okay. And so with all of this done, you end up with a bunch of single variable integrals that you can just plug and chug. Yes?
Would A and B be 0 and 1?
Yes, and I think that was a typo from when I wrote these notes. I've already got it on my to-do list to change. Yeah. 0 and 1, you're quite right, are what the A and the B ought to be. All right, let's do another example. So here, kind of a weird example I made up, highly manufactured, but I've got the unit circle is kind of my, let's just say my property line, right? I've got a circular shaped lot, let's just say. And I want to put a fence around my property. Fine, go ahead. But here's the weird thing. I want the fence to be of a non-constant height. Now, why would I ever do such a thing? Well, maybe I've got a vegetable garden over on the left side. I want the fence to be lower so I don't get shade on my vegetable garden. Perhaps. And then maybe over here on the right side, maybe that's where I'm going to put a chicken coop, and I want the chickens to be comfortably shaded, so I want a higher fence there. For example, right? And again, let's not overthink the realities of things. It's just a hypothetical scenario. For whatever reason, I want my height of my fence to depend on location like this. Okay, so with that said, let's see here. Here's my base of my fence. That's my property line there. The height is going to be like that. How high the fence is. You can see kind of a picture of my fence forming here. And as I make my fence like that, how much area am I creating? What's this area of this, picket on my fence right there? Well, that area is height times width. The height, again, we have a formula for height. The width, length, whatever you want to call it, this distance down here, that's a little piece of my property line. That's a little piece of the curve over which I'll be adding all this up. That's ds. So this picket, this little differential picket, has area that's just h times ds. And adding that up over the entire curve, right, adding that up over the entire curve, we get these integrals. And notice we have a line integral, scalar, line integral, and now we just have to compute the scalar line integral. Everybody with me on the development part there? Okay. All right, so how to do the line integral. I have to parameterize my line. My line, of course, is this unit circle here. Good news, it's easy to parameterize. The unit circle, we've done it before. There it is, our old friend. Right. We take a derivative. That gives me the velocity. We take the magnitude. That gives me the speed. aka our stretching factor. And so now this, we got lucky on how that one turned out. The speed happened to be 1. Certainly will not always be the case, but that's what we then do with our ds. Our ds is our speed, namely 1 times dt. Whoa, what happened there? Okay, that was weird. I don't know what I did, but the computer just switched me over. Okay. Is everybody good? Is my recording still going? Let me just check. I'm sorry. Yeah, okay, we're still good. Is everybody happy? Okay, now again, what's the deal with with x? How do I get rid of x over here? Don't forget the parameterization tells you what x is. You can see right here, parameterizations give you x and y, position, as functions of time. And so x specifically is cosine t. And so we replace x with cosine t. All right. So, so that's all I'm going to say about scalar line integrals. We're going to move on now to a different idea. In the next few minutes, we'll see how far we get. This, at a glance, first glance, is going to look like another scalar line integral question. We're going to be adding something up over a curve, but it's going to turn out to be different in ways that we haven't seen before, and as a result, we're going to have to tweak things a little bit. We're going to get a fundamentally different kind of a line integral. Let's not get too far ahead of ourselves. I hope everybody recalls this idea of work, force dot displacement. Keep in mind, force is intrinsically a vector. Displacement is intrinsically a vector. High school treats these as scalars. That's just a high school point of view, right? But we're treating them as vectors, and as such, we get this improved formula for work, recognizing these objects for what they, in fact, really are. Okay, but this formula, even though it's better than the high school formula, is still a little narrow. This assumes that my force is a constant. It won't always be, right? Look at these vectors here representing forces. They could be wildly not constant, right? So if your force isn't a constant, well, then you can't use that formula. What about the displacement? This formula, we never really considered an alternative, but this formula assumes that our displacement is over a straight line path between 2 points. It won't always be, right? Look at here. What if I'm computing the amount of work it takes to do this? I want to, drive along that road, walk along that trail, whatever it is. It's not a straight line path, right? So again, this formula doesn't really address that. So we're going to try to figure out now a way to generalize this idea of work to a curved path through a non-constant vector field. And you can probably guess the big picture strategy, chop it up, add it up, the whole is the sum of the parts. I'm going to argue that if I take this entire curve and break it up into little pieces, such as this little piece of curve right there, that little piece of curve by itself is approximately straight. Not exactly. Close enough, though. And on that little piece of curve, well, the little piece of curve is small. There's not much room to move. There's not much room for the vector field to change very much. So the vector field it's not exactly constant, but it's close to constant, close enough. In the limit, for the kinds of cases we're going to deal with in this course, in the limit, we can treat the piece as straight and the force as constant. Okay. And then on each little piece, we're going to write down our old formula. We're going to say, for example, on this little piece of curve, we're going to say, all right, here's my position differential. That's my, keep in mind, this is a flashback to chapter 3. You may recall we defined this thing called dx back in chapter 3. This says, based on our linear approximation at whatever point we're looking at. Based on that linear approximation, what is our differential estimate of displacement? It's not exactly right. The curve actually did curve a little, but based on what's going on at this point, our estimate of the displacement is that vector. And so we've got a displacement. We've got a force. Again, approximately constant over this piece. And no sweat. Work is equal to force dot displacement. Right? So on the piece in question here, on this little piece C, that is my formula for how much work. And then I just add that up over all of the pieces. Adding up over all the pieces, let's see here, let me, so looking at the whole curve, right? And we get this expression here, integral f dot dx. Before I erase and move on, let me pause. Everybody see how that played out. Okay, several things to say at this point. So for one thing, notice that this does not look like a scalar line integral. That's weird. This is a very strange construct. This is a very unfamiliar construction. We have never to this point seen a construction where the differential is a vector. Weird. Right? New. A little scary. Likewise, the integrand is a vector. Again, pretty much new, right? So, as previously noted, and it seemed weird at the time, but because our differential and our integrand are vectors, per the pattern of, set by when we use the term scalar line integral, we're going to call this a vector line integral. It's a new construction. It deals with these fundamentally different situations. Oh, furthermore, the product here, that is not a scalar multiplication. That is a vector operation. That's the dot product acting on vectors. So yet a third sense in which we're talking about something that's fundamentally different from scalar multiples. Okay, here's another aspect of this that's different. There's a hidden aspect of this that's different, and that is that if you think of this as the question at hand here, computing the amount of work that it takes to hike a certain path out in the woods, or to drive a certain road from one altitude to a different altitude, whatever. It really matters which way you're going, right? If you're walking out on a hike, going uphill, it's a lot more work than going downhill, right? So, very, very different. So we can't just say, oh yeah, we'll just call this a curve. Importantly, this is not just a curve. This is what we call an oriented curve. It's oriented in the sense that, in addition to being certain points, there is a defined notion of which direction am I going along that curve. And furthermore, not only am I defining which direction I'm going, I have to define what direction I'm going because it matters to the answer. If you go the other way, you get it's really importantly different physical answer. Work is negative if you go backwards. Right? So this is another new thing. If you look back to other kinds of line integrals we talked about, let's take the fence example. It doesn't really matter which direction you go around the fence. The area of the fence is what it is. Whichever way you go. You can paint clockwise, you can paint counterclockwise. Same amount of paint. Right? If you look at mass, for example, how much mass do you get when you add up in one direction versus if you add up in the other direction? Who cares? It's mass. You're literally adding scalars. It doesn't matter. Right? Again, this is brand new concept, sort of a brand new awkwardness. So heads up, when we're doing vector line integrals, curves are not good enough. We need to have an oriented curve. There needs to be an unambiguous indication of which direction are you going, and your tools for computing have to respect that. Let's see here, and I appear to be out of time, so I'm going to draw the line right there, and we will pick up here on well, not on Friday, test on Friday, so we'll pick up here next week. Y'all have a good one. See you later.